Hello, in this video I'm going to go through what is quite a long projectiles question. We got, what was that, 15 marks there, so there's a lot going on and we'll just see different methods, what might be interesting, what might not be. I mean, it could be that nothing is, but we'll see what happens. We've got a competition trying to kick a football to land in a box. Height of the box is 1 metre, it's got width of 3 metres. Right, okay, so they've given us all that on the picture. Student kicks a football at 12 metres per second at an angle of 50 degrees. Right, so we've started off 12 metres per second, 50 degrees. Hits the front edge of the box, yep, as they've drawn on. Model the football as a particle with no resistance forces. Okay, find the time for the football to move from the point where it's kicked to the box, then find the horizontal distance, and then what's the next bit? Oh, if it hits the back edge of the box, so we're just moving everything along. And then explain the significance of modelling the football as a particle. Right, well, we can already say the last bit because we can ignore the dimensions of the football. Because otherwise we don't know exactly where it started from, because we'd have to reduce it down to its centre of mass. We don't know where it started from, and we wouldn't know exactly when it's hit the box. So we can put down something here for ignoring ignore dimensions of the ball. You could turn that into a slightly more fluent sentence than that, but you get the idea if you were writing it in an exam. Right, so solving all of these, let's go for our standard SUVAT approach to begin with. So all of this stuff at the moment is to do with distances. We've got a displacement, vertical displacement of 1 metre. We've got U, so we're going to be going in for UT plus a half AT squared. Because we're after a time anyway, so this seems fine. We can do that in the vertical direction, so we can say 1 is, put the t at the front, t times 12 sine 50 degrees minus g over 2 t squared. So all we've got to do with that is whack it into the formula, the quadratic formula. We're not going to be doing anything more cunning with it because, I mean, look at the numbers. So this is also a way of me padding for time while I'm typing it into the calculator, and that's giving us that t is 1.76 seconds. So that's quite a quick start actually for doing that. I mean, 5 marks seems is one of these generous exam boards. Find the horizontal distance from the point where the football is kicked to the front of the box. Okay, well, we now have to move our attention from the vertical to the horizontal. We're going to actually be doing the same. We're going to be doing the same. Yeah, we want horizontal distance. We've now got the time, so we're going to be using the same thing, same SUVAT equation, but in this case, it's just going to be S equals UT because there is no acceleration in the horizontal direction. So our S is going to be equal to 1.76 multiplied by 12 cos of 50 degrees. So easier to calculate, and that's coming out at 13.576. So let's say 13.6 meters. Right, so far so good. Right, now we're, what is it saying here? Kicks the foot at the same angle from the same initial position, but what speed? Okay, so they've got rid of this 12. They've changed the speed, and we want to hit the back edge of the box. So are we doing exactly the same thing again here? We're doing the same. We're using the same equations. We're just repeating these two in reverse order. So we now know that our S in the horizontal direction is 3 meters further. So we've got 16. Let's go for the slightly more accurate one. 16.576 is the distance. That is going to be, so what was that? That's our S, so that's UT. We're going to want to bring T out of this to put into the other equation. So let's divide by U, which is U cos 50 degrees, because the angle hasn't changed. And that is the time it takes to hit the back edge. And as I say, I've gone for time because we're going to need to sub that in to the vertical version of all of this. So in our vertical, so this is that's horizontal. Worth making a note of that, just so the people reading it can see what we're doing. And then in the vertical, we can do the same thing. We've still got a displacement of 1, and that is going to be u. Oh, we've got the t, so ut sine of 50 degrees minus g over 2t squared. That bit hasn't changed. So now we can sub this t into this t in equation 1 into the vertical one. So 1 equals, oh well, those u's are going to cancel, and we got sine over cos. So we've got 16.576 tan of 50 degrees. And then we're taking off, so we've got the g over 2, and then we've got all of that t squared. So g over 2 u squared cos squared 50 degrees, and then 16.576 all squared on the top. So handily, we've only got one little bit of u sitting around here. So we rearrange to make u the subject, and then just tap everything into the calculator, because our u is going to be equal to quite a big square root of, what are we going to have here? We're going to have a g times 16.576 squared. That's all we've got on the top, and we've got a lot of stuff on the bottom, because we're going to have the 2 cos squared 50 degrees, and we're going to have 16.576 tan 50 degrees minus 1. So we just got to type all of that in, and that's going to give us, God, that's a lot to type in. And we want to have something where it's got to end up being more than 12. So that's our sanity check on it. Nearly there, typing it all in. There's loads of it. 13.2 meters per second. So yeah, so it is more than 12. So that seems to make sense. So yeah, that's a bit of a slog way of going through it all, but it does have suggestions of how we could do it in a different way, particularly when you see what we've ended up with here. This looks very much like our equation of the parabola, the Cartesian format of projectile motion. So let's try this again. Yeah, just with a different approach for it, I think. Yeah. Right, let's have another bash at this, but yeah, doing it in a different way. So if we were going to do, remember, if we're doing the Cartesian approach, we're starting with our parametric equations of x equals t u cos theta and y equals, yeah, I'm going to write it out in a slightly different way, as multiplied by t. So u sine theta minus g over 2t. So the reason I've written it out that way is we've got in the horizontal direction, because there's no acceleration, we're saying that the distance traveled is the velocity multiplied by the time. So that's just fairly basic. That is also s equals ut plus half at squared, but that's just the basic definition for constant velocity. For the vertical direction, we're saying that the vertical displacement is the average velocity multiplied by the time. So there's time at the end. So this bit in the bracket is our average velocity, and it's the average velocity because it's our starting velocity plus plus half the accumulation of the acceleration. So that is our average velocity, and I went through that in an earlier video. We can then combine these. We make the top equation, we make t the subject, and then we drop it into the bottom equation. So that gives us our Cartesian format of projectile motion. So just dumping all of these things in. I mean, this is just a fairly simple rearrangement. Oh, that should be a squared after saying it's simple. Yeah, rearranging everything and then putting it into Cartesian format. So let's try using this, because you'll see this is very, very similar, well, identical really, to what we had in the second part of the question. We rearranged it and we got all of this. So maybe this is going to be a quick way of going about it. So for the first part of the question, we've got the y is equal to 1, x we don't know. That's what we've got to work out. Actually, for the third part of the question, second part of the question, we have to work out x. We've got that theta is 50 degrees, and we've got that u is 12. So we can tap all of this stuff in and work out what x is. We can do y plus. We got an x squared, so we do have to put it into the quadratic formula. So yeah, we can type all of this into the formula, and then it's going to give us what x is. So I won't bother typing it all in because it's going to take ages, and I've already done it, and we know what the answer is. So that's going to give us that x is 13.576. We can then put that value for x along with u and theta into our first parametric equation, which is going to give us what t is. So we've done part 2, now we're doing part 1, and that's going to give us 1.76 seconds. So that's all good. Just put some units on there. And then now for the last part, we've already got the Cartesian format. We've once again got y is equal to 1. We've got that x is 16.576. We've got that theta is 50 degrees. So now we can just solve this for u, which is exactly what we did in the final part of the previous method. This is the equation that was rearranged, and then we just plug in all of the numbers and get out whatever it was, 13.2, wasn't it, for u? So yeah, it's quite nice. I mean, this does seem to have dropped out a bit quicker than the last one. I think what's going to be the difference on this as to why we can use this? Is there a way we can identify that this is going to be useful right from the outset? I mean, there isn't really that much difference, but the fact that we've got so many, we've only got one thing missing from each one of these lists. If you're going to use the Cartesian format, then you need 3 of those values. So we need to have points that we know the object is passing through. So if they were giving us times, and say we didn't know what height we were going to end up at or something like that, then we wouldn't be able to use this approach so easily, because we'd have to go back to our parametric versions if we were dealing with times more often. But if we can just eliminate the times, and we've got our starting speed, angles, and then various points that we're passing through, then that is just completely calibrating our Cartesian equation. So yeah, 2 different ways of going about the same thing. There's still a lot of calculator work on this. This is probably a prime case of when we get on to coding some of this up, of actually using numerical methods to solve some of this, because that's a lot of calculator work, and nowadays who uses a calculator? So we want to be getting this into some code really in order to be getting our numbers out of here, because it's far more secure and reusable. So yeah, let's wrap that one up. I think it's a bit of a bitty question, but this approach with the Cartesian equation doesn't get used very often, so it's worth keeping it in your arsenal.